Hello, Tensor friends. I got an interesting question here. When I was doing some transforms, going from Cartesian coordinates to polar coordinates, I got this question, which went back and forth with a few texts before I finally understood what they meant. And I'm paraphrasing. Why did you use the Jacobian transform on the basis vectors, but not the vector components as they were taught? And you're right, I did not, because I took a shortcut, and I should do that. You should be consistent when you do this. So let's do it consistently, and I'll show you why I didn't do it because it's a lot longer. Okay. So we have some vector in Cartesian the coordinates, which has these components and these basis vectors. And we want to go to a new vector in the polar the coordinates, which has r and theta components, vr, v theta, and these basis vectors. Okay. So we're going to let r and theta be the unprimed the system and the xy the coordinates be the primed the system. All right. So we would write these components in the generalized form like this. So v and the I is in the contravariant position, upper position, right? So this is our only, the free index is I. Excuse me. So on this side, we write our Jacobian and we put the free index in the same position here. So that leaves a lower position, and then we got the prime the system. So this becomes the summation index, right? So what does that mean? Let's let I equal R, right? So VR is equal to, here's our free index, R. So we go R and R. You can't change that. The prime becomes the summation index. So in the first case, it's X. In the second case, it's Y. All right. Now, what does that mean? What does J or X mean as an example? It means the partial derivative of R with respect to X. All right. So what's R? Let's look at our drawing that we used in the video, right? So we have a circle which has a radius, and we can drop a perpendicular to this X axis. So this would have an X component and a Y component. So using the Pythagorean the theorem, x squared plus y squared equal r squared, right? So r equals the square root of that. So we have to take the partial derivative of this with respect to x. I wrote the square root here as a 1/2 because it makes it easier. So we take the derivative of this with respect to x. The 1/2 comes down. We take the derivative of what's inside, which is 2x. Then we subtract a 1, so it's minus 2 over 2. We get a negative 1/2. All right. We simplify that. The 2's cancel. We get x over this, the square root. But what is that? Well, we just saw it right here. It's r. So the partial derivative of r with respect to x is equal to x over r. All right. So we got one piece of this. Now we got to do the same thing again, which is the partial of r with respect to y. Well, we're going to use the exact same logic we did here, except it's y. So we get y over r, right? Because we get the 2y comes out and it goes on the bottom and it's r. All right, so now we got both the pieces here. All right, so now let's make up a Cartesian the coordinate. I chose a 3 comma 4. All right, so we put that in. Now what is x and y? Let's go back to our drawing, okay? So the cosine of this angle is equal to x, the adjacent over the hypotenuse, x over r. The sine of this angle is equal to the opposite over the hypotenuse, y over r. Okay, we rearrange that, take r to the other side, we get x equal r cosine theta, y equal r sine theta. Let's put that back in here. Okay, so we get this, r cosine theta over r sine theta over r, the r's the cancel, and we get this. All right, now what's theta? Well, let's look at the drawing again and use that exact same, the things we just did by saying, what is y over x? Well, it's r sine theta over r cosine theta. R is cancel, sine theta over cosine theta is equal to tangent theta, okay? So if we take the inverse of that, we get that theta equals the arctangent of y over x. Well, what was y? It was 4 because we made it up. What's x is 3. So the angle is 53.13 degrees. All right. So now we've got to put that back into this equation, and we solve all this out, and we get VR is equal to approximately 5. Well, the way I did it was just looking at this. R is equal to x squared plus y squared square root is equal to 5. So that's the reason I didn't use all of this, which is the proper way. You're correct. It is the proper way to do it. But I didn't do that because for me to understand, and I think for beginners to understand, this was really, really the simple. All right. And you would have to do the same thing for V theta, exactly the same, the method. And then you would wind up with all of your components. Now, for the basis of vectors, there's no shortcut, right? So if we wanted to find ER, we would write it like this. So now the R is in the covariant position, so that's our free index. So it's here, and it's here. The summation index in this case is X first case, Y the second case, right? And we know what that means. The partial of X with respect to R, partial Y with respect to R. We put in what X and Y are and differentiate it with respect to R, and we get this. So in terms of the basis vectors, there was no shortcut. I did it the proper way, and I should have done this the proper way the first time and shown you how easy it was to do it the shortcut. Anyway, that's the answer. All right, I hope it helps. See you later.